Hi everyone, this is Gangadhar Teja. I and my friend Rahul are undergraduates in the Department of Electrical Engineering at IIT Tripati. We would like to present the topic Magnetic Susceptibility Weighted MR Phase Imaging of the Human Brain, which was an American Journal of Neuroradiology presented by Alexander Roscher, Marcus Butt, and some others in 2005 April. This paper basically tells us how improved processing of susceptibility weighted MR phase images offers a new means of contrast for neuroimaging applications. It also demonstrates the potential diagnostic value of MR phase imaging of the human brain. Before getting the details of the techniques or methods proposed in the paper to improve the contrast of susceptibility weighted MR phase images, I would like to give you a brief note on what susceptibility weighted imaging is. It is originally called as bold venographic imaging, which is an MRI sequence that exquisitely sensitive to venous blood, hemorrhage, and iron storage. SWA uses a fully flow compensated long echo gradient recall echo pulse sequence to acquire images. This method exploits the susceptibility differences between tissues and uses the phase image to detect these differences. The magnitude and phase data are combined to produce an enhanced contrast magnitude images in SWA. The imaging of venous blood with SWA is a blood oxygen level dependent technique, which is why it was referred to as bold venography. Due to its sensitivity to venous blood, SWA is commonly used in traumatic brain injuries and for high resolution brain venographies, but has many other clinical applications too. If you want more details about susceptibility weighted imaging, you can browse through the below given links. And then the paper starts with an explanation on the importance of phase images. Phase images are basically obtained from the process called phase contrast imaging, which is a method of imaging that has a range of different applications. Phase contrast imaging basically exploits differences in the refractive index of different materials to differentiate between structures under analysis. Phase contrast enables very high resolution imaging, makes it possible to distinguish features a few angstroms apart. And the paper also tells us the importance of phase images. Phase images contains valuable information that can be used in many MR applications. Some of those are phase contrast angiography, blood oxygenation level dependent MR venography, MR thermometry, etc. And the method proposed in the paper to improve the contrast of MR phase images contains few steps, which are like image acquisition, where high spatial resolution T2 star weighted single echo images were acquired in 5 volunteers and one patient with a tumor on a 1.5 Tesla system. And then patient was imaged with the contrast enhanced T1 weighted high spatial resolution, which is mode of 3D magnetization preparation rapid gradient echo, in short MPRAGE sequence. Then post processing was performed by using IDL. Then 3D images were reconstructed by inverse fast Fourier transform. Then phase unwrapping was applied to all wrapped phase images. Then coming to the technique to refine the phase to refine the contrast of phase images contains two steps, which are like a high pass filtering on the unwrapped phase images by subtracting a low pass filtered unwrapped phase images from the original unwrapped phase images. You can uh, it can be given by the first equation where I is the unwrapped phase images and L cap is the low pass filtered operator. Then the unwrapped and filtered phase images H cap of I were further processed by applying a minimum intensity projection MIP in the equation. It gives by M cap to several adjacent high pass filtered phase images H cap of I. From here on, my friend Rahul will continue with the presentation. Thank you for my part.
So, hello everyone. I'm going to talk about the results that are obtained from the previously spoken technique. So, This figure 1 has 4 images. The first image, I mean the figure 1A, is an actual view of an original wrapped phase image, and 1B, 1C, 1D are the axial, sagittal, and the coronal view of the phase data respectively after applying the unwrapping technique. So if you notice, figure 1A appear mainly close to the surface of the brain and near airfield cavities. The large phase changes in the frontal region of the brain, that is the dark areas in the unwrapped phase images, uh, shown here, this one, are caused by the sphenoid sinuses, which create strong static field inhomogeneities in the neighboring tissue. So coming to the increased contrast in the brain MR images, the following figure shows the brain anatomy. So the phase and magnitude images of the same data set, which I'm going to show the following slide, show different characteristics and behavior that can be used as a source of additional information. So if you see figure 2 and 3, these are the regions of the brain. So we are going to concentrate on the parts here, the capsula extrema, capsula externa, capsula interna. Here we see in this, the figures 2B and 3B show face images in which the capsula externa, capsula interna, and capsula extrema can be identified clearly, which has a clear contrast by comparing the anatomic image. Here we have the clear contrast than in the magnitude images of different slices. And moving on, coming to the tumor, the figure 5B is the magnitude image of the susceptibility weighted scan, 5B image, and the MP-range image of magnitude is 5A, which are able to display the tissue, but we cannot see the clear shift in the tissue, which can be seen here in the 5C, which is a face image. So that here we can see the clear detailed shift of the tumor in the 5C of the face image. We can distinguish the shift, which is clearly notable. So coming to the summary, after phase unwrapping in image space and high pass filtering, that is by using the proposed technique of phase images, we can clearly say that phase image display small anatomic structures with high contrast and resolution, such as different parts like small veins, deep nuclei with increased iron content, or even white matter tracts which are not easily visible on corresponding magnitude images. There is also increased contrast between cortical gray matter and white matter because of differences in local cerebral blood volume. Unwrapping the face images in image space, on the other hand, preserves all spatial frequency components of the face information and gives better results in regions of low homogeneity of the static magnetic field. The high pass filtered images, the face images can, however, be combined with the corresponding magnitude images to create a better or bold MR venograms for a better analysis. So the important features like of edema, tumor shape, and the size and their effects on nearby anatomy can be assessed with a single susceptibility weighted scan if magnitude and at the same time the phase data are evaluated together. So to conclude, we have demonstrated the potential of MR face imaging and emphasized that susceptibility weighted face images bear additional information which can be seen in face, especially in the face images, apart from magnitude image, that is not accessible in the magnitude images alone as well. So that's it. Thank you for being patient with us. I hope this is helpful.